Hi there, today I'm going to go through AQA's A-Level Maths Paper 2, Section A from 2019. Section B, the mechanics part, will follow in a later video. So first of all, we've got four graphs and we have to identify which of these represents y equals 1 minus the modulus of x plus 2. With modulus graphs like this, we know that anything inside the modulus must be, when we take the modulus, that makes it positive. So this tells us that this function has a maximum value at y equals 1, and it has that maximum value when the expression inside of the modulus is 0, so when x is equal to minus 2. So we're just looking for a maximum at 1 and minus 2. There it is. Question 2, simplify this expression. So the square root is a power of a half, and we know if we multiply numbers that have the same base, we just add the powers together. So we've got 2/3 plus 2/5, and then to the power of a half. 2/3 plus 2, let's just work this out separately. So 2/3 is the same as 10/15, and 2/5 is the same as 6/15, so that's 16/15. And if we have a power to another power, we just multiply those together. So a half of 16/15, that's going to give 8/15. Okay, each of these functions has a domain of x being all the real numbers. So with that domain in mind, which does not have an inverse, okay, well, let's just try and draw these quickly. So x cubed looks like that. 2x plus 1 is going to look something like that. X squared looks like that. And e to the x is going to look like that. An inverse, well, if it doesn't have an inverse, it will fail the horizontal line test. And what that is if we draw a horizontal line through each of these graphs, and at any point it touches the graph at more than one point, then it fails. And you can see with x squared, that one will fail. Okay, so you might say, well, surely root x is the inverse. Only if x is greater than 0 will root x be the inverse. Okay, so if the domain is all the real numbers, then that one does not have an inverse. All the others, you can quite simply reflect them in the line y equals x, and those will be valid functions with one value of y for every value of x. Okay, obviously if we do that with the x squared one, that's not a function because one value of x has two values of y. Right, these two quadratics have a common factor of x plus 2. Sure that this is true. Well, it doesn't. The common factor bit is a bit of a red herring here. The important thing is that x plus 2 is a factor of each. So just using the factor theorem, we know that that will be true in each case. So we can say for the first function, if we substitute in minus 2, we get minus 2 squared minus 2x plus c. Minus 2b plus c, and that's equal to 0. And in the other case, the other function, we've got minus 2 squared minus 2d plus e, and that's equal to 0 as well. So we can get rid of the 0 and just make the two expressions equal to each other. So we've got 4 minus 2b plus c equals 4 minus 2d plus e. The 4's cancel on each side. If we bring the 2d across, then we get 2 into d minus b, and move the c across to the other side, is equal to e minus c, which is what we're after. Okay, question 5. Now we've got a differential equation to solve, and we need to use the technique of separation of variables here. So we move all of the t's to one side of the equation, so we multiply across the t, and then we move the dx to the other side, so we get ln x over x squared dx, and then we put the integral signs in. So integral on the left hand side is very easy, that's just t squared over 2. And on the right hand side, we're going to have to use integration by parts. So we need to choose a u and a dv. So LIATE, you might have come across this acronym. So we've got ln x here, we've got 1 over x squared as an algebraic term. So this will be my choice of u, and this will be my choice of dv. If I differentiate ln x, I get 1 over x. And if I integrate 1 over x squared, remember that's x to the minus 2, I get x to the minus 1 over minus 1, so that's minus 1 over x. And the by parts formula is this. So I want u times v, so that's minus 1 over x times ln x, and then minus the integral of v times du, so that's going to give minus 1 over x squared. So I'll make that minus a plus in front of the integral. And then I just need to do this second integral. So it's integrating 1 over x squared, but I've already done that before. I know that's minus 1 over x. And then because it's indefinite, I need to put a plus c on there. Okay, so this is the general solution. But I've also got this boundary condition here. So I'm going to substitute that in now. So on the left hand side, 2 squared over 2 is 2. And when I substitute x equals 1 on the right hand side, well, ln 1, log of 1 is 0. So the first term vanishes. And I've just got minus 1 plus c. So c is 3. So I've got t squared over 2 is equal to minus 1 over x ln x minus 1 over x plus 3. And we wanted it in the form t squared equals f of x, so I just need to multiply the 2 across. And I can also tidy it up a little bit by taking out a common factor of minus 1 over x. So I've got t squared is equal to 2 times, minus 2 over x times ln x plus 1, and then plus 6. Right, question 6. We've got a curve in the form a sin x plus b cos x. We're told it has a maximum value of y is 4, and the curve passes through this point here. And I need to find a and b. Well, we know that when we've got a linear sum of sine and cosine, we can write it in 4 different ways, and one of those ways, for example, is like this: r sine of x plus alpha. Okay, and this r is a squared, is the square root of a squared plus b squared. That's how we always find that out. But that's just the amplitude. And because the curve has a maximum value of y equals 4, then that's telling us that 4 is equal to a squared, root a squared plus b squared, or in other words, 16 is equal to a squared plus b squared. Okay. We also know that it passes through the point, so let's use that bit of information, just substitute that back into the equation. So we've got 2 root 3 is equal to a times sine pi over 3 plus b cos pi over 3. Sine pi over 3 is root 3 over 2. And cos of pi over 3 is a half. So if I rearrange, so I've got 2 simultaneous equations here. So the easiest way to solve that is to rearrange the linear equation for one of the variables. So let's say I rearrange it for b. So I'm going to have 2 root 3 minus root 3 over 2a, and then I'm going to multiply by 2. So b is going to be equal to 4 root 3 minus root 3a. So if I then substitute that into the quadratic, I get 16 is equal to a squared plus 4 root 3 minus root 3a all squared. So that's a squared plus, so 4 root 3 all squared, that's going to be 16 times 3 is 48. I'm going to have a cross term, so 4 root 3 times root 3a, that's minus 12a, and then times 2, so that's minus 24a. and then minus root 3a all squared, that's going to give plus 3a squared. So let's rearrange this. I'm going to have 4a squared minus 24a, 48 minus 16 is 32. So I divide by 4, I get that. That will factorize in a minus 4, a minus 2. So I get a is equal to 4 or a is equal to 2. Now, it can't be 4. And the reason for that is if it was 4, that would imply that b was 0. Okay, going back to the quadratic expression. So I would end up with just y is equal to 2 sine x. And obviously that's not what this graph is, because it doesn't start at 0. So that can't be right. So that means that the solution must be a equals 2. And if I substitute that back in, I get 16 is equal to 4 plus b squared. So b is equal to, b squared is 12. So b is equal to root 12, which is 2 root 3. Question 7. Sketch the graph of any cubic function that has both 3 distinct real roots. Okay, so what does that mean? It means it crosses the x-axis 3 times and a positive coefficient of x cubed. Okay, so a positive one has this sort of shape graph. If it was negative, then it has that sort of general shape. So I need to do one that shape and crosses 3 times, so it could go something like this. Okay, part B. So we're given a cubic now, and we're told that p is greater than 0. Show that there is a turning point where the curve crosses the y-axis. So turning point, I want to differentiate the function. So 3x squared plus 6px, and q is a constant, so that differentiates to 0. I want to find where the derivative is 0. So if I take out a common factor of 3x from each term, I've got 3x times x plus 2p. So either x equals 0, which is what I'm looking for, that's crossing the y-axis, x is 0. And we also got x equals minus 2p, which we need for the next part of the question. Okay. So B part 2, it has 3 distinct real roots. Considering the positions of the turning points, find in terms of p the range of possible values of q. Okay, so we've got 2 turning points. So we've got a turning point at x equals 0 and x equals minus 2p. Now the first part of the question also told us that p was greater than 0. So that means that, so therefore minus 2p must be less than 0. And it was an x cubed, a positive coefficient one. So that means that this is the first turning point, because that must be the maximum. And then the 0 one comes after that. So it's going to be something like this. Okay, so a minimum when x is 0, and this maximum when x is minus 2p. Now, if we just substitute back into the equation we had at the start, so let's just write that down again. So it was x cubed plus 3p x squared plus q. So when x is 0, y is simply equal to q. But when x is equal to minus 2p, the y value there will be minus 2p cubed plus 3p times minus 2p squared plus q. So that's going to be minus 8p cubed plus 12p cubed plus q. So we get that. Okay, so these are the y values of these points. So that's 4p cubed plus q there, and this one is at q. So what are the range of possible values of q? So remember, there are 3 turning points. So first of all, we've got that q must be less than 0. Okay? Because if it wasn't, if q was equal or greater to 0, then we're going to have a graph that looks like this. Okay? And that would only have 1. Or if q was equal to 0, then we'd have 2 turning points. There wouldn't be distinct. Well, we'd have 3, but the 2 of them wouldn't be distinct. But also, we can't have the graph being too high. So we've also got that q must be greater than minus 4p cubed from here. Because otherwise, in the same sort of way, otherwise the graph would be too low. And it would go like something like this, I suppose. Okay, so it must be between those values. So you can see that q must be less than 0, but also greater than minus 4p cubed. Right, question 8 is a modelling question. So we've got some data about house prices over periods of decades, and the price going up and up. So apparently in 1970 you could buy a house for £8,000. Wow. And the equation is this. So V is equal to P times Q to the power of T. And P and Q are some numbers to be found. So first of all, and this is quite common in these modelling questions, the first part is just show that this power law can be written in terms of logs. So if we take base 10 logs of both sides, we get that. Then we can just use our different rules. So first of all, we've got a product. So we can write that as a sum of logs. And then we also know that when we have a power inside of a log, we can bring that to the front as a coefficient. Sorry, t in front. So we get that, which is what we're asked for. Okay, and we're going to need that for the next part. So then we've got a graph. So we're given a table. Sometimes you might have to put some of these points onto the line, not in this particular question, but on other years, other papers, you might have to put a few of these on. But we just want to find the values of P and Q here. So let's just write down that equation we had again, which was that log 10V is equal to log 10P plus T log 10Q. And we've just got to identify that this is like the equation of a straight line. So these are my y values, right? That's what we've plotted on the y-axis. T are the x values. That's what's on the x-axis. So then that means that log TQ must be the gradient and log 10P must be the y-intercept. So I can read that one off. So I've got log 10P from the y-axis is just 3.9. So P is 10 to the power of 3.9. And if we evaluate that, we get 7940. And read the question, 3 significant figures. The gradient, well, if I pick 2 points, if I pick that point there, and let's say I pick this point here at 40, T is 40, then the gradient, which is log 10Q, is delta y over delta x. So the y value there is 5.28 at the top. At the bottom, it's 3.9. And then I'm dividing by 40 minus 0, so divide by 40. And that gives 0.0345, so Q is 10 to the power of that. And again, to 3 significant figures, that gives 1.08. So our model now looks like this, that V is equal to 7940 multiplied by Q, which is 1.08 to the power of t. So find the value when it's half, find the year in which the value is £500,000. So we've got 500,000 is equal to 7940 times 1.08 to the power of t. So if you rearrange that, divide by 7940 and then take logs in base 1.08, which you should be able to do on most modern calculators. So we get that. And this gives us 53.8. Now we're starting from the first year was 1970. So the year is 1970 plus 53.8, which gives 2023.8. So in other words, it's during 2023. Okay, so do not round up in this case. The question is, when will it first be worth that? Well, it's during that year. It hasn't quite got to 2024 yet. And then part D, explain whether your answer is likely to be reliable. No, because our data only goes up to 2010. So we've extrapolated the data past 2010 up to 2023. So we haven't got knowledge of what's happening there. And lots of things could happen. So she could change her house, or the housing market could change, okay, it could crash, or prices could go up very quickly, who knows. Okay, so the housing market could change anyway. And then last question on section A, show that the first two terms of the binomial expansion of root 4 minus 2x squared are these. Okay, so we've got 4 minus 2x squared to the power of a half. What I want to do is I want to make this a 1. So I'm going to divide by 4. So I've got 4 times 1 minus 2 over 4 is a half. So I've got that. And if I multiply things together to a power, I can split that up. So I can have 4 to the power of a half, which is 2, and just take that outside. So I've got that. And now I can use the binomial expansion. So the binomial expansion is that 1 plus a to the n is approximately 1 plus na, the first two terms. So I've got, in this case, 2 times 1 minus a half x squared times a half. So this is my half for n. And if we multiply that out, we get 2 minus, and the 2 and the half cancel. So 2 minus a half x squared, which is what I'm looking for. Great. B, state the range of values for which this expansion is valid. Well, the bit that we binomially expanded, we wanted a half of x squared to be less than 1. So we've got x squared must be less than 2 then. And so x must be less than, well, sorry, the modulus of x must be less than 2 then. Root 2. Okay, so then using that, find an approximation for cos x. Well, how does that relate to this quadratic that we just had? Well, if x is small, then cos x can be written as, this is the small angle approximation. It can be written as 1 minus x squared over 2. And somewhere in your answer you should write that 0.4 is small, so this upper limit here. So we can approximate it like this. So we've got from 0 to 0.4 of root 1 minus x squared over 2. And that's not quite what we had in part A, because we had 2 of those was equal to 2 minus x squared over 2. So what I want to do is I'm going to say I've got a half of that then, a half of the expansion. So I'll put the half outside, and then the expansion was 2 minus 1 over 2 x squared. And we can just do that integration quite easily now. So 2 integrates to 2x, a half x squared, that's going to be x cubed over 3, so that's going to be 1 over 6 x cubed from 0 to 0.4. And if I do that on my calculator, then I get 0.39467. So again, just looking at the question to tell me to put it to 5 decimal places. And finally, a student decides to use this method to find an approximation for this integral. Why this may not be a suitable method: 1.4 is not small anymore. That's not a small angle. Okay, so the approximation is not suitable anymore. Okay, and that's it. That's the end of section A. If that's been useful to you, hope it gets you through your exams. If you've got any coming up soon, then please like and subscribe, and I'll have the mechanics part on here soon as well. Okay, bye for now, everybody.